All right. Thank you, ma'am. Thank you so much. For these kind words and inviting me to reach out to this large audience and participants of this workshop. Uh, Before I begin my talk, I will take this opportunity to quickly give an overview of IIT Bombay and our department and our specialization. I'm sure that I don't need to give an introduction to the audience about IIT Bombay. IIT Bombay, which was established in 1958, has been doing number of uh, uh, large-scale national, international level research. We have got QS rankings overall 118, and we have also in the department level, we in the engineering and technology we are 23rd, and um, at IIT Bombay we are basically now among the top three in India. So, if any one of you are coming to Mumbai, you are most welcome, and there are number of places other than IIT Bombay to see around, and possibly you will also see some beautiful places nearby Mumbai. We have Department of Civil Engineering at IIT Bombay, where we have almost 58 faculty members now, and we have 7 verticals. Out of those 7 verticals, ocean engineering is one of them, and I mostly work in the area of ocean engineering. We have master's program in ocean engineering as well as PhD program, other than BTech in civil engineering. So in this, we have participated in various mega scale projects, and few of them are just shown here pictorially. I'll not take much time in this, but just to give a glimpse of the kind of projects and the kind of technical work that we get involved with. And in ocean engineering specialization, we are 4 faculty members, including me. Uh, Another 3 are there. So Professor Balaji, who is currently on deputation as Director, National Institute of Ocean Technology, Institution of Ministry of Earth Sciences, and currently we are 3 who are running the program. And then we are also expecting one more faculty member who will be joining in next 20 days time. So we have quite decent group, I won't say large, and we are also expecting that people who have really done excellent research to really reach out to us and come and possibly join us, so that we will be happy to have them on board as faculty members. In addition to that, I will also urge here that we have PhD program. We request all the uh, students who are envisaging to do PhD, we encourage them to apply, and we have a standard process. I'm sure you will get through this process, and we will be happy to have you on board. As well as those who have completed BTech, they can apply for Masters, MTech in Ocean Engineering. So you will be also on board, and we'll be happy to have you with us. Thank you so much on that. And then some of the research that we have been carrying out on various aspects. These are some of the basic outline of the research that we are doing on different aspects: coastal engineering, offshore engineering, energy, offshore marine renewable energy, yes, coastal structure. So we have a laboratory. We have quite a good laboratory facility. This is something what you can see is a wave flume, and this is another wave flume. So now these wave flumes or the wave makers are completely indigenously designed by us. You can see here the design has been already patented, and we have got this Hydrowave IITB trademark, which is there with us. We have complete system that is starting from fabrication, the control system, everything. So we are also almost in discussion with other institutions where we can give them the support and install it at their places. We also carry out various field studies where we collect a lot of oceanographic data and coastal engineering data that is required for various of projects that we do. In addition, we have been doing several studies, including numerical modeling studies as well as physical model studies. And you can see here typical studies that are created in wave flume as well as numerical model. And we could really reproduce the physical model setup in numerical models and apply it for various aspects. So I will quickly move on. We carry out number of experiments, including offshore engineering, coastal engineering, and so on. So these are all some of the studies which we have carried out on climate related research, where we try to understand the futuristic scenarios. With that, I'll not take much time. I'll quickly move on. I'll possibly touch upon we work on wave energy, blue economy, and so on. So the blue economy, we are now moving towards establishing a center, so which is going to be a center for blue economy, and mostly it will have multiple institutions across the country as well as internationally. Finally, before I end this introductory session or part, I will try to highlight this one, which is very, very important, especially those who are interested to start a startup. So just on Monday, Ministry of Ports, Shipping and Waterways signed an MOU with various four institutions: IIT Bombay, IIT Madras, IIT Kharagpur, and IMU, Indian Maritime University, to set up Maritime Innovation Hub. So IIT Bombay is one of the institutions out of these four to host Maritime Innovation Hub. And as part of this Maritime Innovation Hub, we will support startups. So these startups are going to be supported initially with a seed grant of 10 lakhs. And those who actually qualify and they will be able to show progress, they will go to the next level for pilot scale. And then we will have a support of 60 lakhs. And those who demonstrate in the pilot scale will go to the commercialization phase. That time they will be supported with 100 lakhs, that is almost 1 crore. And this support is not only in financial terms, we will also have connections to all the ports, and whatever they develop, they will be directly connected to the ports for the future expansion and commercialization and as well as business. So this is a very good opportunity. I request all the prospective people who are thinking or have not started, and I request you to start thinking to connect to this and join this marathon. So this is Maritime Hackathon, and the name is called Marathon. So to join this, please go to this link. You can take a snapshot or note it down. So this link, which is given here, https://ntcpwcit.in/hackathon. So that link will provide you this space where you can register. You will also have number of theme areas or focused areas where the startups are expected, and these areas have been obtained from the ports. So it will be really beneficial to the ports, and it is necessary for the growth of our country. So thank you so much. With this, I will possibly end this part of the talk. This is our team who are working with us, and we are glad to have their support with us. Thank you so much. I will move to the technical talk now. Now, let me go to the slide with my technical presentation, which is on wave modeling under high wind conditions. Madam, is this slide visible as well in full screen?
Yes, sir. Yes, sir, it is.
Okay. Thank you so much. So the call came from Sachiko ma'am to give this talk, and in fact, she only decided the topic. So I thank her that she understands the work I do. So based on that, she has aptly selected the topic for me. I hope this topic that I'm going to discuss will be beneficial to all the participants. Before I talk, let me tell you that it is not possible to give a complete overview and details about any topic within just half an hour or 1 hour. So what I'm going to do is just give you a brief of the kind of work that we have done, the kind of work that can be done, and some of the techniques that we have adapted. So my only sincere request to all the participants is you please have look into the publications at a later stage and try to get into more details. So that will give you more idea and more insight. And I'll also highlight some of the aspects that we have done in terms of applications. It's not only theoretical. In terms of applications, I will also highlight, so that we should have a direction always. Whatever we do in terms of science, in terms of theory, we should always take it to public use. So that is something I would like to also emphasize. So in this process, when we talk about high wind conditions, for me as ocean engineer, always the moment we talk about high wind condition, I always think about the extreme events in the ocean. That is, one of those event is cyclone, where the winds are very, very high. Otherwise, also, when the winds are slightly stronger, instead of cyclone, it could be strong winds during monsoon. There are also high wind conditions. They also create some events which are extreme in the ocean. So uh, my focus here will be mostly on the cyclonic wind conditions. So let us first go ahead with that. So first question is, what is the genesis of high wind condition? So when we talk about the genesis of high wind condition, we are talking about this low pressure regions and the convection that happens, and then the flow of wind that happens towards the low pressure region, and eventually there is a kind of spiraling circulation. And these cyclones which are generated, mostly we know that in the northern hemisphere it is anticyclonic, in the southern hemisphere it is anticlockwise, and in the southern hemisphere it is clockwise. So in the northern hemisphere, when we deal with the cyclones, we always see that they are anti-clockwise. And these cyclones, once they're generated, what happens? What is the impact or effect of that? They are going to create some kind of surge. So because of the low pressure, there will be piling of water. In addition, there will be some wind stress, which is going to push mass of water, and that will also pile up the water, and eventually together they will create this surge. So this surge, whatever we will see here, they are not going to stay at a location. They will propagate. So when they propagate when they propagate towards the coast, especially when the cyclones come towards the coast, they are going to be catastrophic. And as you see, the piling of water will also basically try to dissipate or try to spread out on both sides. But on the seaside, it will spread out at over a large region, and you will not find much surge heights for that. But on the land side, you will see that the surge is going to be resisted by the bathymetry or the ground. So that will create piling up of surge, and the height will be very, very high. And this water, when they actually further propagate towards the land, they create devastation. So that is why this is very, very important aspect to understand. Now, in this process, what are the damages? As you can see in these pictures, there are few cyclone impacts that I have shown here. You can see this is super cyclone that happened in 1999 in Odisha. Then this is also again impact of super cyclone. You can see the kind of devastation that has happened. It was really very severe, and at that time we didn't have a very efficient warning system as well. That's why the impact was very high, or we could not really evacuate the public to a large extent. However, over the period of time, you can see Phylin happened in 2013, Cyclone Titli happened in 2018, Cyclone Fani happened in 19. So these cyclones eventually occurred. But over the period, we have evolved with various forecasting techniques, as well as dissemination or warning systems, that is helping us to reduce the damage. So that damage is not only in terms of evaluated in terms of the flooding by visual inspection. As you can see, the damage can be evaluated numerically. The damage can be evaluated using the satellite images. These two images, you can see something which is before, something which is after. uh, those who are in this field, they can clearly identify these patches, which is clearly showing the waterlogging of this area, which is very simply due to the cyclones. And in this case, we have two aspects. One is rainfall, one is surge. So surge impact will happen up to certain extent. Rainfall will happen over a large extent, but it can be evaluated. We can find out. But what is the root cause? Root cause is the wind, strong or high wind conditions. So now, when we talk about this high wind and cyclones, there are recent events which are actually happening due to the changing climate. As you can see, one event that I am showing here is shown on the right side figure. This is showing two cyclones occurring on both sides of India in both the basins. One is in the Bay of Bengal, one is in the Arabian Sea. And these cyclones were almost simultaneously occurring. And the reason why I'm highlighting is the energy. See, the cyclones are not just cyclones, they are actually dissipation, or it is the output from the ocean when the heat content is very, very high. So the ocean is releasing heat and releasing energy. So now the question was why there were two cyclones, which was usually not the case, because the energy was so high and the temperature ocean heat content was so high. That's why the cyclones were simultaneously occurred and they created devastation. Now it is being studied. It has also been studied by various researchers, including us. And if we see the kind of cyclones, you can clearly see that along the east coast of India in the Bay of Bengal, we have more number of cyclones compared to Arabian Sea. But in the recent days, if we see, this trend is also changing. So the number of cyclones in the Arabian Sea is increasing, and the number of cyclones in the Bay of Bengal are not increasing that much. But what we see that the number of cyclones in the extreme category, or very severe and extremely severe cyclones, are higher in number compared to the lower intensity cyclones. That means that indicates the energy content or energy release from the ocean is also very, very high. So we have to really focus and work on this so that we can provide enough support to the community. Just to give you an example and scenario of the global cyclonic conditions, you see here the number of cyclones or tropical cyclones over all the ocean basins. You can see here Southern Hemisphere, Northwest Pacific, Northeast Pacific, then North Atlantic. They are all having very high number of cyclones compared to North Indian Ocean. So when we say North Indian Ocean has almost 6% of the total number of cyclones globally, it may look small. But what is important? Important is this 6% of the cyclones are responsible for more than 80% of global fatalities, mostly due to coastal flooding. So that is where our focus and interest comes in. So we have to really work and increase our forecasting, increase our warning. That will be useful for the public. Now, coming to the analysis that we did sometime in 2015, we also saw that the uh, uh, power dissipative index, PDI, in the Arabian Sea as well as in the Bay of Bengal have increased over the past decades. You can see the energy or the dissipative index was lower earlier, but in the past 1 decade, we could see high peaks. So that indicates that in both the basins, Arabian Sea as well as Bay of Bengal, there is the impact of climate change and increasing temperature, which is already existing. It was established in 2015. And over the recent last decade, we have also seen that it has been observed in terms of increased number of cyclones, intensities, and IMD also validated all these statements, and they are also making the same statement. In this process, let us try to understand uh, the surge. We have been discussing about cyclone, but when it comes to the coast, we call it surge or storm surge. So what is storm surge? As a definition, we can tell that storm surge is an abnormal rise or fall of water level in the sea generated by tropical storm over and above the predicted astronomical tide, or over and above the tide. So when these storms or the storm surge occur, they actually propagate towards the coast. As you can see in this video, as the category of the cyclones increase, the flooding or the impact is aggravated. That is true. That is happening because once the category increasing means it is the wind speed which is going to increase. So the surge finally depends on the wind speed. There are multiple other factors on which it also depends. What are those factors? So factors that are influencing the storm surge are listed here. One of that, as I mentioned, is the storm intensity or the wind force or wind stress, which is again derived product of wind speed. And then we have something called central pressure, storm size, storm forward speed, angle of approach to the coast, shape of the coastline, or basically geometrical features of the coast, then width and slope of the ocean bottom, especially in this case, the continental shelf plays a major role. Local features, there could be local bathymetry, local outcrops, and local site conditions. As we know, the west coast is completely different compared to east coast. When we also talk about east coast, the coast of Tamil Nadu, coast of Andhra Pradesh, coast of Odisha are fairly different compared to coast of West Bengal, where Sundarbans comes in. So the impact could be completely different with different local features. And wind induced waves, so that is also going to be coupled. So it is not only surge. On top of surge, you will have waves which will be generated by the strong winds. They are also going to flood and inundate and impact the structures along the coast. That is what is very, very important to be understood and evaluate. Then we have impact of swells, tides, all that will be there. We will see as we move on. Now, when we talk various aspects, I'll just quickly show these other things. It's not only storm surge which are actually affecting. There are other parameters as we have listed here. So they will all affect. Now, what is important? As we have discussed, wind speed we are focusing and we are trying to understand that how this wind speed actually transferring the energy or transferring the forcing to the water. The surge will be generated or the water is going to pile up or it will create the surge only when the energy from the wind is transferred to the water. And what is the mechanism? It is the interface or the boundary layer. So at the boundary layer, the wind speed transfers the energy from air to water. That is what is very, very crucial. And that if we can represent properly, that will actually solve majority of our problem, or we will be close to very accurate representation of the wind condition in surge prediction. And what is the parameter that we use when we do the numerical modeling or wave modeling? We use something called drag. This is very well known to many of us that whenever there is a flow over some surface, there will be a drag which will occur. Now the question is how well we can represent this drag so that the energy transfer from the water to from the air to water is accurately represented and reproduced. So that is something which people have worked for years. So if you see, this is a formulation given by Garrett in 1977, and the CD drag coefficient was given by this expression. And even now, we are using the same expression for our cyclone surge or storm surge prediction. So typically, INCOIS, Indian National Center for Ocean Information System, is the one which provides this storm surge evaluation and predictions. And the model that they are using is known as ADSUC. And in that model, Garrett's formulation is used for prediction of some storm surge. And how it is used, this CD value comes to this expression. So the tau wind stress, which we use in our governing equation, fluid dynamics equation. So there we will use the value of tau, and tau is calculated as rho a CD u square. U is the wind speed, CD is the wind drag coefficient, rho is the air density, and finally we get wind stress tau. Now I will not get into this details of mathematical detail analysis and all that, but to highlight what or how this CD value has evolved. If you can see, initially the CD was calculated like this, that is linearly varying as the wind speed increases. And people found that it is actually not really happening like that, because if they increase linearly with very high wind speeds, it is over predicting or overestimating the values. which is unrealistic. So that's why they started creating some kind of upper cap. So they had a cutoff value and that they started using. Now, in that, they also found that it is not happening. They created some kind of profile like these data points, and that also was being used in the meantime. But however, these were in research angles, and this never was implemented in the models. In the meantime, there was one study by Powell. You can see here these bars and the points that was obtained by an experiment carried out using some flights through the cyclone. So they conducted the experiment and they measured the drag coefficients, and it was found that it is not actually increasing, it is reducing beyond certain point. So that means initially it increases, and at certain wind speed, the drag value is going to have a peak and further it is going to reduce. So this is what is very, very important. So this pattern clearly demonstrated that there is some problem in the physics that we are not able to capture in our numerical modeling. So a study was carried out by us in this direction, and that study considered this model called wave boundary layer model. So what is this wave boundary layer? Wave boundary layer is the layer in which mostly the processes driving this drag are present. So if you see, we will have some boundary layer like this. Obviously, it is not similar or to the extent of atmospheric boundary layer. It is much smaller than that. And you can see here the waves will be present. The sea spray or the water particles which are basically sprayed during the wave breaking and so on are going to be present. Then you will have other turbulence in that zone. So all these factors are going to play role. Now, are we considering all these factors in our modeling and representation? That is what is the crucial factor. So this wave boundary layer model we used and we resolved, and some of the aspects that were not even considered in the earlier wave boundary model, we included that, which we called it as enhanced wave boundary layer model, and then we used it for our analysis. Before, I will not obviously take you to this wave boundary layer model and details of that. I will not bore you. It is not possible to also explain all this in this short time. But let us accept that we will have a model called wave boundary layer model. What we do in that, initial surface viscous stress is given, then we resolve this turbulent stress, wave induced stress, sea spray effect, then the total stress vector and friction velocity is calculated and that is given, and then we have the wind vector profile. In that, we will check these parameters, and finally we will get this parameter called CD, and there is one parameter called Z0 which we will obtain. Eventually, these are used to obtain the final value of CD. So our interest is that once we get this value of CD, that we can use in our numerical models what we have been using earlier. Instead of Garrett's formulation, we will use this CD for our calculations. Now, in to do wave and circulation modeling, we used these two models. One is ADSRC, one is SWAN. ADSRC is advanced circulation model, and SWAN is a wave model for the near shore, but now it has been expanded for the deeper water as well, so it can very well simulate. So ADSRC and SWAN coupled model was used. In this ADSRC, what we get? We get the velocities u and v in two different directions, that is meridional and zonal directions, and the water surface elevation. These three parameters we get from ADSRC. And we don't have 3D here. It is a 2D model. The depth, it is a depth averaged numerical model. So we don't get the vertical velocity. It is considered as average. So then you have SWAN model where we get the wave outputs, where we get the wave height, wave period, wave direction, all that we get. So it's a coupled model. In this, what happens? The advantage is the effect of wave is also given as input to the circulation model, and effect of circulation is also given to the wave model. So it is a realistic scenario which can be generated. And in that, we are giving the CD value that is obtained from this wave boundary layer model. So it's a kind of iterative process. So first we do this ADSRC simulation, ADSRC plus one simulation. From that we get some wave spectrum. that we do some parameterization and then give it to this wave boundary layer model. Once we get the updated CD, that we use again in the AdCircons one to get the final search value. So this we carried out and studied. And in this process, these are the governing equations which we used. And in this, as I explained, where are we giving the wind inputs? We are giving here. So we are giving this tau Sx or the stress due to wind that is given here. And these are other shear that is due to wave, due to bottom friction, all that will come in. But wind inputs are going to come and given here. And similarly, we also have some wave action balance equation where we have the source term that is due to the wave growth that also is going to be calculated using this tau. Now I'll move on instead of going much deeper into this mathematical expressions to tell you what we did. We considered two cyclones. One is cyclone Thane, another is cyclone Varda. And both these cyclones we considered and we studied using this wave boundary layer model and the improved wind drag coefficient. And we simulated and we found that we are able to predict the significant wave height better, the surge was simulated better, so everything was better. And how did we do that? We considered the IMD and INCOIS measured data for these events and compared our results, whatever we observed. So we found that they are giving better when we considered improved wind drag coefficient. We compared our water level elevation and at all the different locations. This is at Innor, this is at Nagapatnam, and we compared all these values for various locations. And we also compared this, we did the statistical analysis, which also again established our conclusions. In this process, we compared various other models. As you can see, we used the wave boundary layer model. There are other models given by different formulation, and we found that wave boundary layer model is really performing well. And that we considered for further studies. This is where we considered the deep water location. BD11 is a deep water buoy, which is used for comparing the output. And this is wave rider buoy at Pondicherry. So that's at a coastal location. So both in deep water as well as along coastal locations, we could really estimate the surge and waves and in a better accuracy. So this publication is available, details are available here. It is published in Ocean Engineering. In case you are interested to go deeper, you can refer that publication and try to understand. In case you have any concern, questions, you can always reach out to me. Then we developed this improved wind drag method. So what we did, we considered 30 different cyclones which span across the globe at different in different basins, different intensities, so that we can really try to see whether we can capture all the different cyclones and different categories, everything, and how this wind drag coefficient can be estimated for different cyclones. What we did, we considered different categories. As you can see, wind speed 31 to 43 cyclones, 41 to 55 cyclones, 51 to 60, 12 cyclones, all that we considered. The idea was we found that those cyclones which are more in numbers, we considered slightly more of those cyclones and accordingly other cyclones. So all these different cyclones we considered and calculated the CD value, drag coefficient for them. And when we calculated, we did plot all these data points over this graph. As you can see, these black dots, they basically represent CD values for each data point. We had more than 1 lakh data points, and that we plotted in this plot and created this or drew this best fit line or the polynomial fit. And we found the third order polynomial fit is actually fitting best to this data points. And that third order polynomial fit is represented here. So this polynomial is very, very important or useful for implementing in the numerical model. So the process that I have shown earlier, we can reduce that process and save time. I will also show you that in another slide. So this method or this formulation, what we developed, we call it improved wind drag method or IWD method. Again, that work has been published in this Dynamics of Atmospheres and Ocean. One can refer from that. So I will move on. So we tested again after developing this IWT method. We tested at various cyclones across the globe, and we found that they are really performing well. I'll not spend time on that. But what I wanted to show here is we could see that IWT method has basically overestimated the significant wave height, measured significant wave height by 2 to 7%, whereas other methods, there is a Gizlema method that underestimates around 14%. The Garrett's method is overestimating by 40%. So the idea is we should not underestimate first of all, because underestimation can lead to under design of various aspects, which is not acceptable. Overestimate is okay, but too much overestimation will lead to unnecessarily overburden financially. So that is why, or it could also have other false warnings and impacts. So we have substantially reduced the overestimation in terms of significant wave height, in terms of the total water level or elevation. So that's what is shown from this study. The time aspect. So far, all the models, they were using only this portion, and that this section will take, let us say, X amount of time for simulation. If we do all this process, then the time required is going to be almost 3 times. So when we develop this IWD method, we don't have to go through this. We are directly using that, and we can now reduce this computational time, and we can have same computational time what is being consumed now with much higher accuracy. That's what we could develop, and that has already been implemented in this ARSAC model. The student who was working at completed PhD and then went on to work with the core group of ARSAC in US, and he has implemented that in ARSAC, which is going to be released very soon. And these models or improved models will be used by all the agencies. So that is what is a major contribution from our side. In addition, I will quickly uh, talk about effect of pre-existing wave climate on this storm wave and surge modeling. What is that pre-existing wave climate? So most of the times what we do, we uh, generate some kind of cyclonic wind field and give that as input to the basin or the ocean surface. But there will be already some wave which will be existing before the cyclones do arrive. There will be swells which will also be propagating from far off southern Indian Ocean or from different zones. So are they really important? So that is what we try to look at. So what we did, we tried to superpose both these winds. So we considered the pre-existing wind as inputs and as forcing, as well as the cyclonic wind overlaid on that. So that merged winds condition were tested to understand the effect of that. So I'll quickly move on to explain you the graphs here. You can see here we have three different graphs. One is without wave boundary condition, that is WO WBC. Then one is with wave boundary condition, that is WWBC, and one is observed. So we can see here clearly that when we estimate the significant wave height, we don't find much of a difference except this tail portion. We don't find much of a difference. So fine, we are anyway capturing the peak, it's acceptable. Now come to wave period. You can see here the wave period is substantially different if we don't consider this forcing or the pre-existing wave condition. And similarly, here you have significant wave height for another deep water location, and this is again mean wave period for deep water location. So we can see that wave height is accurately represented all through, not only in the beginning, also in the tail portion, and mean wave period is very well captured if we consider the pre-existing wave climate. That is also seen in the wave directions. You can see here in case of wave direction is completely distorted if we don't consider the pre-existing wave climate. So why these are important? Because when we design various offshore facilities or coastal facilities, the forcing that is going to come is calculated based on the wave characteristics, that is wave height, wave direction, wave period. And these values should also be accurate. So when we try to calculate forces during storm surge, and so it is necessary to consider this pre-existing wave climate. That's what is the conclusion from this study. And you can see here that is also published in Ocean Engineering. And if you are interested, you can again go through this paper. Now, While studying these things, I focused on only wind speeds. Now, I also mentioned there are other parameters which are important. This is one of the study where the effect of coastal geometry was studied. As you can see, one of the cyclone was considered, and this was hypothetically varied with different approach angle. And a coast was considered that is along Chennai, which is basically a concave coast. So the phenomena or the process could be different for a convex coast, which is protruding outwards, and a concave coast, which is basically bent inwards. Now, why we have considered a concave coast first? Because when this inward, there is a possibility that high amount of surge is going to take place. So that's why we thought we'll go for that. And we considered different transects as the cyclones are coming from different direction. You can see the bathymetry could also vary. The transects along these 5 tracks are shown here. They are completely different. So the depth is going to vary so much. Obviously, the impact on the surge is going to be different. That is what we also investigated. In addition, when you have this kind of concave coast, the cyclone I, if it is located at this pivot at the center, and we have also discussed in the beginning that cyclone is going to be anti-clockwise. So that means there will be a push of surge on the right side of the cyclone, and there will be a pull on the left side. So most of the water is going to gush in from the right side and goes out from the left side. Now, in that process, if we have the direction changed, then that will have impact on the total surge because the amount of water that can actually go out or get released is going to be reduced in some condition. So we investigated all those mass flux analysis, and finally we found that the maximum storm surge inside a concave coast occur for approach angle of approximately 75 degrees. So that is what we could establish, and that is required because when we want to predict and find out what is the possible surge at a particular location, we don't know. The cyclone might come and hit the coast after 2 days, and they may change the directions at any point of time. So tentatively, we can actually consider the cyclone approach angle as the maximum or optimum angle which will generate maximum surge, and then predict it and be prepared with. So that is where this is going to be very, very useful. This work again has been published in Ocean Engineering. Further, we also investigated the effect of cyclone intensification. Now, cyclone, they will start with very low pressure region, then they will go to deep depression, deep depression, then cyclonic storm, very severe cyclonic storm, then extremely severe cyclonic storm, and super cyclonic storm. So this is a stage which is going to happen for intensification, and it could be different for different cyclones. And when we see this intensification, they can intensify at any point of time. Depending on the ambient condition, atmospheric conditions, this intensification happens. And this intensification can continue for intensified cyclone, can continue for 24 hours, can continue for 6 hours. It could just intensify just 6 hours before the landfall. It could intensify 24 hours before the landfall. There could be different permutations, combinations. So we tried to understand that. So what we did, we analyzed all the cyclones along the Bay of Bengal, in the Bay of Bengal basin, and we tried to figure out how this intensification happens. So finally, what we did, we concluded that we will understand like this. There are cyclones. This scenario A is basically the cyclone is intensifying 24 hours before the landfall and continue to propagate with this intensified intensity, and even 6 hours after the landfall, the same intensity will continue. Second scenario, the intensification happened 24 hours before and continue up to the landfall. Then next, it happens 24 hours before, but it again, the intensity drops 6 hours before landfall, and so on. And these scenarios are basically instantaneous intensification for 6 hours. So it intensified at before 24 hours, and after 6 hours, the intensity came down. And this is again intensified before 18 hours, and immediately after 6 hours, the intensity came down, and so on. So we studied all this, and then the investigation we could find that the peak maximum water levels are going to vary for different intensities. And we understood that in the KG basin, there are different, we have considered KG basin, Krishna Godavari basin. The reason is the Krishna Godavari basin is going to be considered, or there are a lot of potential for offshore explorations, oil and gas. So there could be various structures and they need to be designed. So that's why we wanted to understand that effect very, very carefully. So with this, we understood that the effect is going to be different, and the intensification is also going to make much of difference. So we need to investigate and find out which is going to give the worst possible scenario. That again has been published in Climate Dynamics. One can again try to look at that for more details. Now, let me come quickly towards some of the direct practical implementation. So this source-induced coastal flooding, we also did some analysis with different climate change scenarios. So this work was done when RCP was being discussed, or we were with the AR5 scenarios. So which is representative concentration pathways. Now we are not talking about RCP, we are talking about SSP, shared socioeconomic pathways. So these RCP scenarios were considered for the study how the climate change impact is going to have on the flooding. So what we did, we considered RCP 4.5, which is a moderate scenario, RCP 8.5, which is a extreme scenario. So RCP 4.5, we considered 7% increase in the wind speed. RCP 8.5, we considered 11% wind speed. And we did carry out the study for various category of cyclones. And in this study, what we did, we considered a number of locations. This was done along the Odisha coast. So one location is Gopalpur, Puri, somewhere in the mouth of Devi River, then Vitarkanika, and so on. So these locations were considered to have landfall of the cyclones at these places. Now, if the cyclone is going to have a landfall at Puri, then what will be the flooding for different intensities and different scenarios? So in that aspect, if you look at this, this is a map which shows flood depth along Paradip coast due to extremely severe cyclonic storm landfall at Puri. So landfall is happening at Puri, but we are looking at the flooding along Paradip. I have already mentioned that the cyclones are going to be anti-clockwise. So on the right side, there will be more gushing of water towards the land. So as we can see, when the landfall is happening here, there will be flooding here, but there will also be huge flooding along Paradip. So that is what we are trying to study. So different locations we have considered. As you can see here, this scenario is basically the regular scenario we have at Puri. At Paradip. Then this is again with RCP 4.5. This is with RCP 8.5. As you can see, the intensity increases. So similar maps were prepared for number of cyclones, different categories, different landfall location, different RCP scenarios, and they were generated and created so that in case of emergency, in case of a cyclone which will happen of that category, this kind of maps can be used for by the policymakers and administrators. So this is again another one which is having landfall at Gopalpur. This is landfall at Gopalpur with super cyclonic storm. This is extremely cyclonic storm landfall at Puri. So we have created such maps all along. And we did not stop there. Then there was a requirement from Odisha State Disaster Management Authority to find out the cyclone shelter locations where they wanted to construct cyclone shelters. Now, where they will construct to get to that solution, we carried out studies. What did we do? We carried out numerical modeling studies. Of course, in this case, we have considered tsunami as well, cyclone as well as tsunami, both. And based on the flooding scenarios, we created some kind of zones. So for each district, you can see here, this is not district, this is a block. So we have gone up to the block level. So we have created zone maps or zonations. So this zone is basically red color is no shelter zone. Nothing will be constructed in this zone. So people have to evacuate away from this zone. Then this is the zone 1, zone 2, zone 3, which are varying with their vulnerability. So then we considered number of parameters like population, settlement, road network, water body network, then the zones and the flood depths and so on. Everything was considered, and finally we calculated or found out the cyclone shelter locations. based on the National Disaster Management Authority guidelines. So these shelters or locations were again prioritized. We have thousands of shelters which are required, but which one to be constructed first? So we also gave them the priority, and based on that, whenever the fund is received from government or any source, they can allocate based on that priority. So this is another work which we did. And in this process, we also gave them the design, complete design for the cyclone shelter, considering all guidelines, all aspects of NDMA and structural stability. So this is some application work I'm just trying to highlight so that you can realize. Uh, I'll just quickly skip this. This is another work which was again application. There are a lot of sensitive coastal installations. Let me take an example. Let us say there is a coastal nuclear power plant. So it's a sensitive one, and we don't want any flooding to happen. And that if there is a flooding, that can create havoc. Nuclear radiation can create a lot of problem. So in such cases, we have to ensure that there is no overtopping even during storms and tsunamis. So for that, we did a design. There were already some available various profiles which are used for arresting the overtopping and over the protection wall. So now all these measures we analyzed, we found that none of them are actually completely stopping the overtopping. So we carried out a lot of various combinations, and finally we ended up getting this profile, which is called as forward backward two radius profile, and we have given some dimensions as well in this. This kind of profile can be adopted on top of this protection wall, which obviously has to be designed with respect to the conditions. And then if we put this kind of protection wall or ground wall, forward backward two radius profile wall, then we can completely reduce the overtopping. So that is what numerically also we observed. You can see here the black line is showing no overtopping at all. So the idea was when the wave comes, it is overturned and thrown back into the sea instead of allowing any overtopping on top of that. Now, further to that, there are a lot of focus and push for nature-based solutions for various coastal protection. So we also carried out studies in case of surge and tsunami. What will happen? There will be a kind of bore which will propagate towards the coast, and that is going to take any kind of debris or any item that's all lying. It will be floating and going towards that. So we carried out a study to understand how these debris are going to impact various structures, and if we put some kind of vegetation like that shown here, how they will also act in case of such events. That also were tested experimentally as well as numerically. Both we did. So that is going to be very useful for various coastal protection studies using nature-based solution. This work was published in Applied Ocean Research, which can also be referred. I'll skip this slide. I have already explained. Further, we did another work that is on climate change impact on coastal waves and coastal stability, where we basically simulated waves in the Southern Indian Ocean as well as Bay of Bengal, Arabian Sea, all that, and impact of those waves were also tested along the coast, how they will vary with climate change scenarios, and what will be the longshore sediment transport. Because of these waves, the sand movement or the sediment transport is going to be altered if there is an increased wave condition or wave height and direction. So we observed all that and we prepared finally the kind of coastline stability maps. This is given by Central Water Commission based on historical data. And what we did, we created similar maps based on the study for 2011 to 2040 scenario and 2041 to 2070 scenario. So how these coastal zones are going to behave with different condition like stable or accretion or erosion. However, this is a very large scale or coarse study. More refined study needs to be carried out for each state and each coastal region so that they can be useful for various project implementations. These works were published in a number of journals, International Journal of Climatology, Climate Change, and so on. This work I will possibly quickly touch upon extreme wave impact forces on offshore and coastal deck structures. So whenever the surge happens or tsunami comes, they are going to impact this kind of structures which are going to be along the coast. Although there is a huge gap between the water surface and the deck, but in storm conditions, these waves, first of all, the water level is going to be rising. And then on top of that, the high waves are going to also come and hit the decks. Usually in the design, those impacts are not being considered. So that is what we wanted to look at. And the effect of that can be seen clearly how the damage can really occur. So we used a model, numerical model called REAP 3D, which is written in C++, and it uses the governing equations, Reynolds average, Navier-Stokes equation. So using these equations, we did a lot of studies, and based on the output that we obtained, we finally derived some coefficients, force coefficient. This is a horizontal force coefficient. As you can see, that is given by this expression. And you can see in this expression, we need two parameters. One is S, one is H. What is H? H is the wave height, S is the air gap. So air gap is intentionally considered here because over a period of time, we may have settlement of the structure that needs to be considered. Over a period of time, the sea level is going to rise. So the impact of sea level rise will also be accounted for in this S. So now the field engineers can use these two parameters and easily calculate these force coefficients. And once they find out these force coefficients, then the expression is very simple to calculate the horizontal force as well as vertical force. And that force can be considered for designing the structures. So that is what we did for various types of waves. One is solitary wave, which basically represents tsunami scenarios. This is non-breaking waves. We did for breaking waves. And similarly, we also carried out studies and gave these expressions which will be useful. I know I am running out of time, but in a minute, I'll just quickly tell we also carried out this evaluation of climate models' ability in simulating nearshore wind speeds. So wind speed, as we have been discussing, is the crucial input for all these studies. So are these climate models giving or are we using the proper wind speed? So what we did, we considered a method, we developed a method rather, I would say, which will consider all different time scales. So daily mean, annual cycle, annual mean, seasonal scales, then spatio-temporal variability of all this were considered. And then we developed something called total relative score. So using this total relative score, we evaluated all 77 climate models. We carried out it for CMIP 5 models. We again carried out for CMIP 6 models. So this is a typical methodology which we used for evaluation of these models. And after evaluating these models, what we observed that there are some models which are performing really well and some models are not. So you can see here, you can refer these publications, but you can see here, some of the models are very high performing that have very high TRS value. So we did it for CMIP 6 as well. And from that, we finally arrived at this conclusion that this model MPI, ESM1, 2, HR, AWI, CM1, 1, MR, these are the models which are really giving good wind conditions for the ocean. Please note that we have carried out the study for ocean and land. So different models are working well for the ocean side and different models are working well for the land side. So they can be used accordingly as per the evaluation that we have done. With that, the study was also extended to carry out wave analysis along the coastal location of India. Number of locations were considered. Based on that, the wave characteristics were also evaluated. And these evaluated wave heights or wave characteristics were used for evaluating future design wave heights. So as you can see, different scenarios, SSP 2.245, SSP 585, SSP again, yeah, for both the scenarios we evaluated and we found that how it is changing over different scenarios or different future conditions. This was extended again to understand the sediment dynamics or the coastal profiles, coastal impacts for various locations. This is one of the locations where we have, I have shown the field studies are being carried out to understand the coastal profiles. And with that, we carried out this, we used this methodology to conduct shoreline evolution. So over a future period, how these shorelines are going to be evolved, that also evaluated using numerical model as well as empirical formulations. So I'll skip these things. I'll not spend time, but I would just quickly mention that we are also working on this impact of or improved forecasting of tropical cyclones using coupled ocean atmosphere wave models. where the role of marine heat waves is being studied, role of various aspects like MJO, IOD, and so is being investigated by one of our student, Amit. Finally, there are studies which are carrying out this hybrid winds using WRF model and parametric models. And they are also concluding that this WRF model is possibly supporting or enhancing the wind evaluation. And that has been tested by some of our studies that is shown here. And this study has shown that a coupled model wind speed or hybrid wind speed is going to be useful. So that is something to look at. And with this slide, I will end. That is, there are four different sources. One is we can get the wind from the satellites. We can get the wind from weather research forecasting models. We can get wind from reanalysis data. We can get wind from parametric vortex models. So all these, can we bring them together? And finally, can we evaluate some cyclonic wind speeds, which will really help us to improve the forecast and improve the analysis in a better way. So this is a question that I'm leaving it to all the participants and listeners. So to think upon and come up, and there are number of ways nowadays with a lot of techniques, we can possibly integrate all these inputs and come up with something useful, which will be really good. With that, Jai Hind.